So I welcome you all in the second part of the fourth lecture of this CAPSS seminar series. Just a small reminder that this talk is being live streamed in our YouTube channel Nature as We Unfold It, and I would kindly ask you all to turn off your microphone if you are not talking and follow your host. So over to Shreya. Thank you.
Thank you, Prachita. So, good evening, everyone. Once again, I welcome you all to the fourth lecture of the series Nature as We Unfold It seminar series of CAPSS. This is the second part of the fourth lecture delivered by Professor Sibaji Raha. The first part being delivered on last Saturday, and we had a good discussion after the talk. It was really interesting, sir. Today, we shall continue with the interesting topic named the evolution of philosophies behind the quest for physical laws. The talk is basically going to be an oral presentation, as sir has said that there will be no slides this time, and I request you all to patiently listen to the talk, and I hope you will enjoy listening to the speaker like last time. And if you have any questions or comments that you want to discuss during the talk, you can do so in the middle of the talk as well by raising your hand, and please wait patiently for your turn. So this we have decided to introduce in this lecture only, so that this session is more interactive. So please, sir, now you may start. And I had already introduced you last week, so I think this week there is no need for introduction. Thank you. You can start now, sir.
Yeah, hello. You can all hear me, I hope.
Yes, sir.
Okay, yeah. This time I decided to dispense with the slides because, as I mentioned last time, my motivation in giving this talk is to use you all as a sounding board. Whether the ideas that I'm proposing really make any sense or really appeal as possible questions to a general group of people who are not directly involved in pursuing them for their own research. For example, last time at the end of my talk, I think Shukriyo asked a question that what did I mean by insisting on a separation between laws and principles. Since those last Saturday, I have been looking here and there to see if anybody has actually tried to make a definition distinguishing between laws and principles. I must admit that I haven't found any other author, but the general principle or the general sense in which these terms are used lead me to believe, again through examples, that laws usually have a scale built into them, whereas principles don't. And that's precisely why, even within the given domain of validity of a law has to be limited, whereas principles are more general. Let me take an example of the gauge principle. You all know how gauge principles arise. Gauge principles arise primarily in the context of Maxwell's equation. You see that the Maxwell's equations are kind of invariant under certain symmetric transformations, and you see the utility of that by making a very important contribution towards decoupling the coupled equations of the auxiliary descriptions, namely the potentials. You all know that the potentials are not the measurable things, it's the fields which are. And the fields, your transformations on the potentials should be such that the fields are left unaffected. But the purpose of doing this gauge transformation is to ensure that the coupled wave equations for the scalar potential and the vector potential, they can be decoupled and solved easily. They can be made into ordinary decoupled differential equations. And that was the utility of the classical gauge transformation. But when one talks of gauge principle, one sees that these principles are not confined to the classical domain. They apply also to the quantum domain, in fact, in the same form. And as a result, the invariance under the symmetry transformations becomes manifest. And that precisely is something which was realized not very early on, but towards the middle of the around 1960s, 63, 64, when quantum electrodynamics was just becoming very fashionable and quantum field theory was coming into existence, coming into full glory. And one of the biggest puzzles of quantum field theory at that time was that why did Maxwell's equation remain valid in the quantum domain exactly in form? Where were the quantum effects? If I could get the same results from classical physics and just use them in quantum mechanics, what was the need for quantum mechanics and electrodynamics? And that was one of the biggest questions of the whole theory of quantum electrodynamics. And that answer primarily was provided, and I want to set the historical record right here, that the true credit for this work should go to George Sudarshan. The discovery of quantum optics through the use of coherent states. You have all seen coherent states. Coherent states are classic quantum objects, quantum states, but they look very much like classical objects. And the reason primarily is that they don't have a fixed number associated with them. They are not Fock states. So that's precisely why they behave very much like classical fields, although they are truly quantum objects. And you can recast all of quantum electrodynamics in terms of coherent states, and that's why the correspondence between classical field theory and quantum field theory, at least for the electrodynamic processes, becomes well established, and then the whole principle of gauge invariance finds a meaning in quantum mechanics. And last time I told you that Einstein spent a very good part of his life, in fact, a major part of his life, trying to unify classical electrodynamics and gravity. He did not succeed primarily because there was, during his lifetime, no consistent gauge principle associated with gravitation. But on the other hand, in the late 50s, when the quantum processes like weak interaction, like strong interaction, became experimentally established, there were attempts to find gauge theories associated with those interactions. And precisely that's what is done by the Young-Mills formulation, Young-Mills fields. The difference between the Young-Mills field and the electromagnetic field, as far as the theoretical gauge principle, probably some of you will have heard, but others may not have. Gauge group, which corresponds to these transformations. If they are non-commutative, then they correspond to Young-Mills field, whereas for electromagnetism, they are commutative. But with that distinction apart, the principle of gauge invariance holds for both electromagnetic, strong, and weak interactions. So that led actually to the formulation of the unification of electromagnetism and weak interactions, which is now called electroweak interaction. And to some extent, the strong interactions, which also has a gauge symmetry, the local SU3 symmetry, as the strong interaction incorporated in this, and that's what gives rise to standard particle formulation, standard particle interaction theory, the so-called standard model. And much aimed almost exclusively at establishing what this standard model is, what the parameters of the standard model are, arithmetic accuracy, and even more accurately, we try and find whether there is any deviation from the standard. So that's what we talk about. Next generation experiments, leading to beyond this standard. This is indication of the standard model, indication of quantum chromodynamics with the electroweak model, and quantum chromodynamics matter from our standard philosophy. I tried to impress upon you last time that the history of development of physics is in some sense synonymous with the history of development of the detection techniques. And with quantum chromodynamics, we first made, in fact, there was another watershed shift, a paradigm shift in our philosophy when we started accepting quantum mechanics. I mentioned EPR last time, probably not. So I should talk about the EPR now. EPR experiment, the Einstein, Pordowski, Rosen experiment, is essentially the starting point of the Bohr-Einstein dialogue that I talked about last time. And after that dialogue, Einstein essentially proposed what is known as this Gedanken experiment, or a thought experiment. And what he said was that within quantum mechanics, if we talk about a measurement being synonymous with the collapse of the wave function, because until then, because of superposition, all states were possible, but when I make a measurement, the entire wave function, the superposed thing collapses to that particular state of that measurement, and so that's why the result of a definite result of the measurement comes out. And what Einstein suggests is, suppose I have a very high spin zero object will decay into two particles, two fermions. So it could be a spin half and a spin minus one. And these particles, this spin zero particle decays, and the two daughters separate away from each other. And I make measurement on one of them at a point which is far, far away from the other point. Suppose I make a measurement in Washington, D.C. of the spin of one particle with one of the daughters. Then just by conservation principle, I know that the particle at the other end, somewhere in Europe, has to be the spin down. If I found a spin up in Washington, in Europe it has to be spin down. But there was no time for the spin up particle to tell the particle spin which is in Europe that you better go into a spin down configuration, because I'm being detected with a spin up. So does that mean that causality, and suppose the situation is such that they are not within the same light cone, these two particles, then I'm violating causality. I'm sending signal faster than the velocity of light. And this is a Gedanken experiment. That is something which is really making, opening up directions of new thoughts. And if you like, there are even within our own borders, there are better experts at quantum entanglement than I am. But if you like, on future occasions, we could talk about the implications of quantum entanglement and what we do understand in quantum entanglement and what we don't. Especially interesting in that context is something which I'll tell you is a possibility. We talked last time about why the energy time relationship, the delta E delta T, cannot be thought of as a correct or kosher uncertainty relation. And I mentioned to you that That is because we don't know exactly what a Hermitian operator for time would be. People have been able to find that yet. In fact, there is some development in that direction. I must say that great thinkers off and on have over many decades, in fact centuries, postulated about the nature of time, where does time come from, and as a result of that they try to understand what the physical meaning of the arrow of time really is. We say that the second law of thermodynamics essentially implies an arrow of time. But what does it actually mean? Whether philosophically it's some stable concepts or not is something which has remained unclear and unexplained over centuries. But I'll tell you of an interesting anecdote. That anecdote has to do with the so-called quantum field theoretic equation, which incorporates quantum mechanics and general relativity. This is an equation called the Wheeler-DeWitt equation. And the Wheeler-DeWitt equation is actually a very complicated equation, not easy to decipher or work with. As a graduate student, I had to grapple with it primarily because I was taking a course from Rice-DeWitt. So he was very fond of, intrigued us to a large extent. So I'll tell you, Rice-DeWitt said that he wrote this paper after a struggle of almost 3 years. It took him more than 3 years to bring it to a publishable stage. He sent it to Physical Review, who sent it to John Wheeler for refereeing. And in DeWitt's words, Wheeler sat on it for almost 9 months. After 9 months, he grudgingly approved it for publication, saying that he didn't quite understand it, he didn't quite agree with it, but he didn't find anything wrong with it, so he allowed it to go through. Then he was probably deeply intrigued by it, so he started thinking about it in his own time and wrote a review article for a semi-technical journal on this particular paper. Didn't tamper with the physics or didn't add or subtract anything in terms of content to this work. But it was that popular article which found people's attention much better. And so it started getting called Wheeler-DeWitt equation. So be that as it may, Wheeler-DeWitt equation in its original formulation did not have time. A friend of mine, friend meaning we were in graduate school together, he finished his PhD a year later than me, Bill Wooders, he and a colleague of his did some kind of formulation to the Wheeler-DeWitt equation and concluded that time is an emergent phenomenon. And that actually opens up the door for discussing a very interesting aspect. This interesting topic is what is emergence. As the name suggests, emergence means something comes out. Something emerges. And the history of physics since, if let's say, uh, starting with the early concepts of the atomistic theory, be that the Greek picture or the atomistic picture of Panad, where we believed in the reductionist picture. So a consequence of the reductionist picture is that if I start with the basic ingredients and follow laws to build up larger and larger structures, or build up physics as we know, by progressive steps, I would be able to explain the entire structure of the universe, the entire material world. That was the origin of the atom theory. Now, in this reductionist picture, one of the axioms is that I do not get properties built up which are not predicted by the laws. So it's the laws which tell me how to combine these various components. And once I combine them, the laws will tell me how this conglomerate will behave. But emergence means that something untoward, something not provided for within these laws comes out. A new property arises. So that is a deviation from the reductionist approach. Now, is this the first example of an emergent phenomenon in the physical world? Well, in life we know biology is an emergence from chemistry. We still don't know how life really came about. What are the laws of chemistry or physics? The energetics, the reaction kinetics, or what have you, which gave rise to life. So in that sense, life is truly the best example of an emergent phenomenon. Now, if time is an emergent phenomenon in that sense, we would really need to revise many of our ideas about the physical world. But that is something which I really digressed a bit in order to just bring about something which promises to be an extremely interesting topic for the next several decades. But let's get back to the question of measurements that we are familiar with and that are continue to be current as of now. So let's come back to the issue of quantum chromodynamics. And in quantum chromodynamics, we actually make a major deviation from the kind of measurements that we were all familiar with. Now, in classical measurements, I can actually track the particles, I can see them, and I can handle them in some mesoscopic sense. In the subatomic world of subatomic particles, we know that we don't necessarily see them directly, but we see them through primarily their electromagnetic interactions. For that, we know that we actually detect these particles in their free states, the asymptotic states. And it is only for these asymptotic states that the S matrices are defined. If I cannot define the asymptotic states of particles, there is no way I can write down a scattering matrix. And I wouldn't be able to analyze the actual quantum processes that happen. So that means whether I see the particle or not, I should be able, for a meaningful independent measurement, I should be able to bring that particle in isolation. I should be able to make a configuration, but that particle is so free of any other companions that it's effectively a free particle in its asymptotic state. It was in the 60s of the last century when we first made a deviation. That deviation was again in the context of the quark model. You all know what the quark model is, so I will not go into deep details about it. We know that the quarks, according to the phenomenology as we understand so far, all strongly interacting particles, or all particles which do not exclusively participate in weak interactions, and by that I mean electrons. So all other material particles have a fundamental structure, that is to say, they are built up of particles which don't have any form factor. So in that sense, they're point particles, and these point particles are quarks and antiquarks, and their their bosonic mates, the gluons. Now, so far we have not been able to find any form factors for these quarks, so we believe that they are point particles. The most curious thing about these quarks is that in order for the phenomenology of strong interactions to be properly accommodated within the context of these models, we have to conjecture that these quarks and antiquarks have fractional electric charge. Fractional electric charge, you all know from your studies of electromagnetism that electric charge is quantized object, and the E over M ratio is very well measured. So out of that, it's unusual to expect that the electric charge can be fraction of 1 unit of so-called accepted unit of electric charge. See, in principle, it could have been overcome. In principle, one could have said that the electron actually is 3 units of the quantum. So the quantum is not E but actually 1/3 E, call it E prime, so that the electron charge is 3 E prime, and so on. But the principle of phenomenology is that you want to do with the simplest possible assumption, and it has to be a consistent set of assumptions. In fact, once again, an anecdote which I can repeat is, you all have heard of Hans Bethe, of course. Hans Bethe was essentially the person who encouraged me and in fact induced me to enter into the field of field theory for strong interactions. Once somebody asked Hans Bethe that how does one do fundamental physics? You all know that Hans Bethe got his Nobel Prize for his work on fusion reactions in stars. So Hans Bethe thought for quite some time. We were just amused because we sort of knew what the answer would be. And then he finally said, shut up and explain the data. So in that principle, we have to explain the data, and if the quark matter required that the electric charges should be 1/3 units, then one must look for them. There must be sufficiently accurate experiments which will distinguish between the fractional charge and an integer charge. And after the proposal of the quark model with the integral charges, 1963, the first time it was Yuval Ne'eman and independently Murray Gell-Mann. There were feverish activities everywhere, all over the world, to find objects of fractional charge. One or two experiments claimed that they had found them. Among them, one professor from the university in Kolkata. But largely, the overwhelming consensus of the international community was that fractional charges don't exist. But, and so much so that Murray Gell-Mann, even though he was the proponent of the quark model, in mid-60s, whenever there were conferences and people talked about the quark model, and if there was any hint of in the speaker's attitude that these quarks were physical particles, Murray Gell-Mann would really rag them right, left, and center, and just make fun of them, saying that you don't understand that these are actually just mathematical constructs. They've got nothing to do with the real physics. He was very quick to change his attitude once the deep inelastic experiments, the deep inelastic scattering experiments at SLAC were conducted. And you know that the result was that in these experiments, it was established that protons also have three, I'm just being very, very simplistic and just skipping all the details, that for example, a proton was indeed a combination of three hard scattering centers, just like the Rutherford atom picture, the Rutherford experiment. And the form factor matched if one assigned electromagnetic form factor, if one assigned the appropriate fractional electric charges to these scattering centers, and if you calculated them, you would say that, okay, there is agreement with this. And that was essentially enough to believe that, yes, these quarks are physical objects. They are they live within the hadrons. They have fractional charges. But somehow or other, the interaction among them is such that they will never come out. The so-called principle of confinement. And the physical picture which people try to impose is the concept of color confinement, the color singlet configuration, and this again is an attempt, a very conscious attempt to come up with a field theory which would be a gauge theory, namely a Yang-Mills theory. And effectively, you can see how the attitude shifted. The Yang-Mills fields were recommended in 1953-54, and while the deep inelastic, the quark model was gaining credence, and the deep inelastic scattering experiments were proving them, were essentially giving a lot of foundation to them. The electroweak unification was being worked out. And as a result, the temptation to create a field theory which will also explain strong interaction was too much, and fortunately it was successful. So that's why now we say that the standard model has been born, and you expect that if one can extend this even further, one can say that the symmetries which drive the electroweak interaction and the symmetry which drives the strong interaction, the quantum chromodynamics, could actually be subgroups of an overall overarching group, a single group. And the simplest of that could actually be the so-called special unitary 5, SU5 group. That's where the role of experiments arises, in the sense that when we have this electroweak interaction, and by using the gauge principle, we know that in order for this picture to work, there would have to be certain gauge bosons who would combine in a certain manner to give rise to the massive vector bosons of the theory. Massive vector bosons characterize this theory, the electroweak theory, primarily because unless they're massive, the weak interaction would also be long range. We know that electromagnetic interaction is long range because they are mediated by the photons, and the photons have zero mass. On the other hand, the weak interaction has a very small range, and if you just do a back of the envelope calculation, you know that the mass of the bosons which will mediate them should be of the order of 100 GeV. So that's why people started looking for these massive bosons, W plus minus and Z. And that was the crowning glory of the SPS program of CERN, bringing Carlo Rubbia the Nobel Prize. Now, by the similar token, what you see is that and the way to see these bosons is not by detecting them in isolation, in their asymptotic states. Even though they exist in asymptotic states, you don't detect them actually as single particles because they are unstable. They decay. And it's through their decay products, by reconstructing the tracks and extracting their mass, the mass of the parent particle, that you conclude on the existence of these heavy particles. And that's how the Higgs was discovered, which was taken as the final definite proof of the Standard Model. Now, I mentioned this grand unification scheme, the SU5. The SU5, whenever one has an overall symmetry, because of the gauge principles, these symmetries imply a spectrum of the particles that populate this symmetric space. And their interactions, which are consistent with the postulated symmetry, make predictions. For example, one of the predictions of SU5 was that the proton, our most beloved, the most stable hadron, baryon, would not be very stable. It would have certain decay channels. So that's why the 70s and 80s had very large scale activity the world over to look for the proton decay. And in such experiments, what happens is that you never can say that the proton does not decay. What you can do is you set limits on their lifetime. And in most experiments, the lifetime that you deduce came out to be much bigger than the lifetime of the universe. So there is no way to conclude the proton does decay. If you had seen a decay product, then of course the issue would be different. I can tell you that in this context there are two candidate events which were detected at polar gold fields which have not been conclusively shown to be false. But statistically, bulk of all other experiments, almost all the international activity yielded that the proton lifetime must be much, much bigger than the lifetime of the universe. So these two are relegated to the archives of history of physics as something irrelevant. So the search for exotics or beyond the Standard Model does go on. The most recent effort which has been undertaken and which has not yielded the result that people had desperately hoped for is the existence of supersymmetric particles. If supersymmetry had existed, then one would have found some very natural explanations for dark matter and so on. Be that as it may, the LHC did not succeed in showing any hints of supersymmetric particles. And as a result, his next generation, the EHC, is built to act as a Higgs factory as well as further search for supersymmetry. Supersymmetry, in spite of its apparent non-discovery, is physics in the mainstream in the sense that it does predict experimental signatures. It does tell people what to look for, where to look for. That they have not been found there is a different issue, and in fact that is very interesting too. If you find what you are expecting and what you are looking for, it is satisfying. It establishes your theory. But if you don't find what you believe should be there, and you are convinced that you have looked very, very thoroughly, and you have not just missed it, then it's actually a very interesting situation. Then you know that some of the concepts that I started out with was wrong, so maybe I have to go back and refine. And that's precisely what the whole goal of physics is. So, making wrong predictions, coming up with ideas which do not pan out experimentally, is not something to be despondent about. That is, in fact, the objective of physics. So it's fine to make mistakes. It's fine to make predictions. But the criterion is that you have to be able to make predictions which are experimentally verified. Unfortunately, the same criterion cannot be applied to the other very fashionable field of physics, theoretical physics, namely string theory. It explains a lot of things, but it does not predict anything which can be experimentally verifiable today or in the foreseeable future. Be that as it may, the other example that I mentioned at the beginning of today's talk was quantum entanglement. And quantum entanglement is something which certainly appears to be much more counterintuitive, much more esoteric or bizarre, quote unquote. Yet, the experiments aimed at establishing the effects of entanglement have been carried out. The aspect experiments are something which are really a marvel. And there are many other experiments on quantum mechanics which are now in the offing, in the planning. And I think this is something which is really exciting new physics that awaits us through these studies. And my advice to the Scholars Forum, to the CAPSS Scholars group, is that get Professor Dipankar home to talk about these experiments that are either being carried out now or are in the planning, because in my opinion, the results of these experiments will certainly open up very new ideas to pursue, not only in this basic quantum mechanics, but also in high energy physics, and even cosmology. Because we have seen examples of what quantum entanglement in mesoscopic systems and statistical systems, which have not yet been explored in depth, can have implications in the cosmological exam. And many of the questions that theoretical physicists have been grappling with, namely the origin of dark matter, dark energy, and so on, could indeed find answers in our understanding of entanglement. And that is something which is a very, very challenging chapter waiting to be delved into. I think this is a good point to stop.
Thank you, sir, for the very nice talk. So I would like the audience to ask any questions if they have any. Professor Raha. So it seems that no one has any questions. Am I audible actually? Hello?
Yes.
Yeah, I can hear you.
Okay. So let me check the YouTube streaming so that we can know that whether there are any questions there.
Well, I have a question. If you can hear me.
Yeah, yes.
So you were talking about that. Hello, sir. So you were talking about that we are always looking for the gauge theories whenever we are going from, suppose, from weak interaction to strong interactions, in order to, so that we can unify everything, like for a SU5 group, as you say. So is this the only? Is this the only reason why we are looking for the gauge theories, or there are other physical implications, or maybe what will be the physical implication if we have everything under a big symmetry group? What are the benefits, or why we are so eager to have this?
If you recall how the gauge transformation entered physics, yeah. Hello?
Yes, sir. Yes,
Hello?
sir. It's fine.
Yeah. As I was saying, that the way gauge transformation entered physics was in the classical domain, tackling Maxwell's equations, and effectively one saw that by using these gauge transformations, one could leave the physical parameters unaltered, but in the auxiliary fields, the wave equations could be decoupled. You know that in Maxwell's equation could be written in a much more compact form by writing the scalar and vector potentials and eliminating the electric and magnetic fields in favor of the potentials, right?
Yes.
So once I write down the wave equations from these Maxwell's equations in terms of the potentials, the wave equations become coupled. And coupled differential equations are very, very difficult to solve, as we know. The utility of the gauge transformation was that they decoupled. So effectively what it means, the actual rigorous definition of a gauge principle is that I can look at the effects of interactions of fields. Let's start with the Lagrangian theory. And why Lagrangian again goes back to the work of Feynman. That Lagrangian formulation gives me the best transition from classical to quantum through the path integrals. Now, if I have a Lagrangian theory, then the free Lagrange fields can actually be allowed to develop interactions among themselves on the local scale through the localizing of the symmetry. So I have a Lagrangian with a global symmetry. When I try to localize those symmetries, the free fields develop interactions among themselves through the aids of various bosonic fields, scalar and vector. So it is this principle of localizing, gauging is effectively localizing the symmetries. And that's how we end up with a local field theory with interactions. Go back to your lessons of electromagnetism and see how, because of these local gauge transformations, the minimal coupling and the covariant derivative ideas arise.
Mm-hmm.
Okay?
Mm-hmm.
Sir, in this respect, I have a question. I mean, I have a query, right? Actually, what is gauge field? I mean, gauge is there are certain symmetry in nature, and we have calculated in field in space and time.
Yeah.
So, can we safely say that gauge field actually connect the space and time with the symmetry?
No, that's too simple. In fact, in the jargon of field theory, gauge field is the massless field.
Yeah.
And it's effectively it's synonymous with the massless vector field.
Yeah.
So effectively, once again, you see, because electromagnetism is the gauge theory that we know and understand very well, the nomenclature is also fashioned after our electromagnetism to a certain extent.
Okay.
So that's why, as long as the bosonic fields, the gauge fields are massless,
Yeah.
we call them gauge fields. In the standard Weinberg-Salam model, because of the Higgs and the symmetry breaking, you combine them to make the massive fields.
Yeah.
Don't call them gauge fields anymore. The photon remains the gauge field. Okay?
Okay, sir. Thank you, sir.
Sure.
Any more questions from the audience? Okay, so if no, let's thank Professor Raha once again for delivering a wonderful talk in our seminar series. And with this, we conclude our talk for now. Thank you, sir.
Okay, thank you very much.
Thank you.
We thank everyone for joining us today, and please be with us, because on 31st we have another very interesting talk that will be delivered by Professor Ajit Mohan Srivastava. As you all know, he is an excellent speaker. So till then, have happy puja, have happy festivals. Goodbye.
Puchita,
Yes?
one more request from me
Yes,
is
yes.
that there are some seniors from Bose Institute, belongs to Bose Institute, that Anirban Lahiri and
Yes.
Tomal Mukhopadhyay.
Yeah.
Could you please invite them to join this discussion session?
As a speaker, you say?
Maybe they can, if you request them, maybe they can deliver
Okay.
deliver-
We will surely look into that. Thank you so much for that. We will
just
do that.
connect to them.
Yeah. Thank you. We'll look
Okay.
into that. Thank you, everyone.
Okay.